Hello again. Let's talk about spatial isomers. The spatial isomers are where the bonding shape, the bonding between the atoms is the same, but the shape is still different. If we take a double bond, like this double bond for example, it's the double bond would be in this plane. So double bond would be out here and down here. Because it's an sp3 hybridized carbon at this center and this center, the molecule must be flat because the p orbitals have to interact, and this bond cannot rotate anymore. Then we can have two isomers of this molecule, one with the two hydrogens, so this is 1,2 dichloroethane. Just to go back to our naming, this version has both of the chlorines on one side, so the green is chlorine, white is hydrogen, and this version, if we flip it, has one chlorine on the bottom and one chlorine on the top. So let's draw that. So this is how we would draw it, once with the two chlorines on the same side of the double bond, and once with the chlorines on the opposite side of the double bond. And because double bonds cannot twist, these two compounds are not the same as each other. This is important because this compound might behave very differently from this compound, because these chlorines are comparatively large and they interact with each other. If we have even bigger groups on the molecule, so we could have an iodine on here which is bigger than chlorine, it will interact with this other iodine, and there'll be a force trying to bend these bonds, which will make this more reactive. Another way of stopping bonds from rotating is to make them into a ring. So if we have a ring of carbon atoms here, okay, don't worry about the colors, I ran out of molecules in my set. You can see this ring is somewhat floppy because the bonds can move, but we can't rotate it fully through without breaking something. In my set, without breaking something. In reality, we can't get the bond to go all the way through in a small ring without breaking the bond and reforming it. If the ring was very large, it would be floppy, so very large rings can turn inside out, but small rings, 6, 5, 4 and 3, can't flip configuration very easily. What we can also see is the thing that we saw last time, that my six-membered ring, because it's tetrahedral carbons and they don't fit, it sits naturally in a shape like this, with one of the carbons up and one of the carbons down. I can flip it, it's a little bit difficult to do. I can flip it and have them both up. Those are called the boat. This is the boat and the chair configurations of a six-membered ring. If we take these two red carbon atoms and give them a chlorine each, we can have the same situation where the two chlorines are either on the same side of the ring, upwards or downwards, or if we take one off and put it on the bottom, they're on opposite sides of the ring, and we can see that it's not possible to convert one of those to the other because these bonds no longer rotate. Usually we can say if they're substituents on a double bond, if they're on the same side, they're called the cis, this is called the cis isomer, and if they're on opposite sides, they are the trans isomer. Trans by being opposite, cis is on the same side. The other type of spatial isomers are optical isomers, and this is an example. It's a little spring. And if you take a spring or a screw, we can see that it's wound in a certain direction. So if I look down the screw axis, this particular one goes away from me in a clockwise direction and comes towards me in an anti-clockwise direction. And no matter how I turn it, if I turn it over, it does the same thing. So if we take a screw thread, a piece of screw thread, if we take a normal right-handed screw thread, there is no way to convert it into a left-handed screw thread without completely starting again. The other example that people often use is reflections. So I look strange to me on these videos because I'm seeing something that I never usually see of myself, which is my direct image. What I normally see if I look at myself is my reflection, which is not the same. There is no way to convert the reflection of a person into the normal shape, the normal version of a person, by moving it around. You have to reflect it again. So where does that come into effect in molecules? If we take a carbon with 4 different substituents on it, so this one has a green atom, a white atom, a blue atom, and a green atom, then this atom center is optically active. What that means is that this carbon can have 2 forms that are not the same as each other. To help me to explain that, we can hold it by its hydrogen here and see, if I point it towards you, that we go green, red, blue in that direction. If we take another one and hold it in the same direction, we can see it also goes green, red, blue, because these are the same molecule. However, if I swap 2 atoms round, so in this case I'm swapping the red and the green, but it doesn't actually make any difference. If we look at this, we can see that if we hold them by the hydrogen, we get a reflection of each other. So these 2 molecules are now a reflection of each other in a horizontal plane between my 2 hands. If I rotate it, then it's still a reflection of itself. If I put them on top of each other, we can see that there is no way of moving them around to get them to be the same. Even though there are all of the bonds are single bonds, they're free to rotate. The only special thing about these is that there are 4 different things on the carbon. To look at this with the carbon, with the hydrogen at the back, is a relatively good way of doing it. So if we take this case, so this type of image of a molecule with one of the hydrogens at the back is very handy for us to be able to identify which of the potential shapes that we have. So if we take an example with fluorine, chlorine, and bromine on there, and we label them in order of mass. Whoops, let's get rid of this. 1, 2, and 3. We can see that in this case our circle is going clockwise. If we organize it so that the 4th bond is going away and it's a hydrogen, so it's effectively 0, it's the lightest one of these 4 substituents. If we take the lightest one, we point it away from each other, we can look at these and see relatively simply that this molecule has a clockwise direction of mass as they go up. If we swap any 2 of these, it will be the opposite. So let's do that. Let's swap, I don't know, let's swap the bromine and the chlorine. So let's have FBrCl and the hydrogen going away. Then our fluorine goes to chlorine, goes to bromine, and we have an anti-clockwise rotation. So now there's a warning. That anti-clockwise rotation has absolutely nothing to do with what we also see, the rotation of light. So what do these optical isomers do? Why are they called optical isomers? They have a special property. If we take light and we put it through some sunglasses to make it plane polarized, so as you know, light is a wave, and it's a wave with 2 vectors. It's a wave that has an electric vector and a magnetic vector at 90 degrees to each other. If we take light of only one direction, so with, in this case, the electric vector vertical, and we pass it through our compound, Normally what happens is nothing at all. Our light goes through and it comes out exactly the same. If we take our light, however, and we pass it through a pure 1 optical isomer, it will rotate this plane of the light, so it will rotate the direction of polarization of the light to a different direction. That's why they're called optical isomers, and it turns out that each isomer rotates it in a different direction. A good way of thinking of it is this spring, or now this is a piece of jewelry, but is of a spring or a spiral. So we have a molecule that's behaving very much like a spiral, and the light interacts with the spiral and is slightly rotated. Unfortunately, this does mean that there are multiple descriptions of which direction our molecule is. The first one being the direction that it rotates the light, which is either in a right-handed direction, which is called dextro from the Latin for right. It rotates the light in a right-handed direction, or levorotatory, which rotates the light in the left-hand direction. This gives us the old names for molecules such as L-lysine and D-lysine, rotating the light in opposite directions. However, as I just said, it's important to remember that that is not related to conventional naming for the molecules, which gives priority to the masses of the elements attached to the atom. We'll go first of all to one of my favorite textbooks for students. It's called Organic Chemistry with a Biological Emphasis by somebody called Soderberg, Tim Soderberg. It was free for a very long time, and that's why I tend to use it. It's available online. You can download it. You can have a PDF. I usually get it from here, from chemlibretext.org. If you search for it, you can find it relatively easily. And if we go down here past the introduction part, we can see conformation and stereochemistry and structure and bonding, which is the subjects that we were just covering. So this is another book on Chem Libre by Roberts and Caserio, and just like any other organic chemistry course, if we look through pretty close to the top, stereoisomer of organic molecules, which covers the same topics in a slightly different way. If you prefer videos, have a look on my YouTube channel. I've saved a few, or links to some. One by Professor Dave is particularly of interest. It shows a way of identifying or not naming these chiral centers depending on which way round they are, using different types of ways of drawing them. Right, that'll do for me.